Okay, so I will be speaking about bootstrapping descriptors for non-Euclidean data, and hopefully it will become clear how the bootstrap comes in and so on. Let's start with a guiding example, principal nested spheres, which is essentially a dimension reduction algorithm for spheres where you find a nested sequence of subspheres, dimension 1 at each step, and at each step you minimize the sum of squares of geodesic distances of the points to the sphere, and then when you have found a best fitting sphere, you project down geodesically and do over until you reach only one point. And now, of course, this begs the question, what about asymptotics and consistency? P and S can be seen as a sequence of M estimations, so we have at each step an M estimation, but every estimation step depends on all the previous estimation steps. So for each single step, the asymptotic theory is known, and it's fairly generic. But what about the asymptotics of the whole sequence, and also of a single parameter from the sequence? For example, only the ultimate mean point here. Why are we actually interested in that? In some cases, this is an example. So we have this blue data set, which is concentrated along a circle, this red data set along a circle, and if we simply take the intrinsic Frechet mean, we will find that it coincides for those two data sets. We get a very broad distribution of p-values as you would expect. We cannot distinguish them, so we cannot reject the null hypothesis that these have the same intrinsic mean, but they very clearly have different nested means, so a different final point for P and S, and they also have a very different geodesic, so S1 space for this P and S procedure. So in some cases, such a nested procedure can actually give better results than simply taking the intrinsic mean in a manifold setting. Okay, right. So what I will do now is briefly present the setting and outline or give a vague idea of how the consistency and asymptotics work, and finally get to defining the t-square test, of which I just showed you results, but of course those results are absolutely not meaningful if we don't have asymptotic normality, because then we won't know the distribution, the asymptotic distribution of our t-square statistic, which we use for the test, right? So we we define a very general framework, which is much more general than the PNS, the guiding example I presented, of a sequence of separable topological spaces, parameter spaces, Pj, where we have some loss functions, and we start out with a data space, and every point in a parameter space gives rise to a subspace of the next parameter space in line. So the Pj minus 1 here. So we start from Pm, from the highest level parameter space, and then go down step by step. And also it defines a subspace of Q in our case, but it need not. It could define any kind of space. The only important thing is that we have some projection map from one estimator P here to the next estimator S. But these can represent any types of spaces or objects you like. So we need not have nested subspaces. One could also take, for example, the tangent space PCA, where we first map from a manifold to the tangent space and then to the principal components on this tangent space, right? And these are, of course, two subsequent estimations. Okay, so we call this whole sequence of parameters the backward nested family of descriptors. I usually like the word descriptor better than parameter, because what we're doing here is most of the time non-parametric, but one could also do it parametrically, and then there's parameters and parameters, and so yeah, let's so here yeah, therefore we call this a family of descriptors, not parameters. And we can define this space of all these families, where, of course, we have to make sure that every next descriptor is essentially just embedded in the descriptor before, or in this space of descriptors before, yeah, we can define a kind of concatenation of projections, and in our case, it just projects down step by step from the highest dimensional sphere, codimension 1 at each step, until we finally reach the endpoint. And we can define a distance measure between these families. So, right, and then we can, of course, define population and sample descriptors, and we have to keep in mind here that the previous estimation comes in because we have to take the row Frechet function for the corresponding subspace which we estimated before. So actually here we have distance functions on different spaces, right? Because for a sample we will project through a different sequence of spaces than for the population. And this is something we have to keep an eye on. And this is the difficulty to show that this whole family, although we depart to another space in the first step, still asymptotically converges. Right. Yes. So we have this usual setting where we make some technical conditions, and then if all these technical conditions are satisfied, which they are for the guiding example of PNS, we can show asymptotics, consistency and asymptotics. And the first type of conditions are the generic M-estimator conditions we already know for normal M-estimator asymptotics. And then we have two new types of conditions, namely, first of all, the projections have to be well behaved in a certain sense, so that we don't blow up once we estimate another space. And lastly, that the charts have, so the coordinate charts for the backward nested family have to separate, have to factorize, so that we can project down to the subspace that corresponds to a single descriptor, like, for example, only the nested mean in the sequence and ignoring all the rest of the descriptors. Therefore, we need obviously our space to factorize. Okay, and the standard conditions are uniqueness of the population descriptors, some Heine-Borel property. We need a uniformity property for the row Frechet. No, not Frechet, the row distance function, so the distance function of data and between data and descriptors, or subspaces, if you will, and relativity, which essentially says that the Frechet function should not fall asymptote against the minimal value in infinity, but for compact spaces as the spheres in our guiding example, this is automatic. And then we need generic differentiability conditions for the asymptotics. And here we have to introduce charts for the asymptotics, or we do introduce charts. One could also do this in a coordinate-free setting, but we do it with charts. And we need some kind of sort of uniform continuity of the gradient and Hessian in expectation. It's not exactly that, but roughly that. And now the conditions on the projections. We need that if we project from one subspace to another one, and they are close enough to each other, then the subspace S on the subspace P, which we project to the other subspace P prime, should then the projection of this S to the original S, and also doing a kind of ping pong projection, so projecting S from P to P prime and back to P. This will usually not lead to the same S, but it should still be close by. And then we also need some weak triangle inequality for sequences, convergent sequences of subspaces and subspaces in this sense. And these conditions on the projections will actually allow us to do essentially, if you will, the induction step. Okay. And finally, the factoring charts, as I said, having the full parameter space for the full family, we want this to separate into theta, which is our parameter of chart corresponding to our parameter of interest, and xi, which is all the rest. And this can be written in terms of a commutative diagram like this, as usual. Right. So now to state the theorems, as we're sort of pressed with time, the slides will be much more crowded than I can actually explain in detail. So we have strong consistency, and to prove this, we use an inductive scheme. We start with the highest level parameter space where this is known, and then we go on inductively. The central limit theorem also has to take into account all the previous estimations, and there we use Lagrange multipliers to do this. So we essentially say that each subsequent step in this estimation, in this iterative estimation, depends on the estimation results of all the previous steps, and doing this with these Lagrange multipliers. So in the first that the that the sample Lagrange multipliers converge against population Lagrange multipliers, and so on. Yes, and finally, if we have additionally the factoring charts, we can also show asymptotic normality for only one of the descriptors and not only the full family. So first of all, we show asymptotic normality for the full family, but then if our parameter space factorizes, we can just project down because, we essentially marginalize the Gaussian distribution here. Unfortunately, due to this very convoluted procedure, it's basically impossible to get closed forms for the covariance matrices, and therefore we use the bootstrap to get covariance estimates for our t-square statistic. And now the question is how to what to do with the quantiles. We can just look up the known t-squared quantiles because we are asymptotically t-squared distributed, but for small sample sizes it can be helpful to also bootstrap quantiles. Yes, and we can I just so we propose two different procedures. One would be to do a bootstrap on the pooled two samples, and then just mix through the samples. And the other would be to not mix the samples, but bootstrap from each sample separately, and then center the bootstrapped vectors in the chart. And of course, the first one is somewhat problematic, as we see for this example here. Right, these two have the same nested mean, but very different geodesics. And we will see if we mix the samples, the geodesics will be all over the place. So for the pooled samples here, we get p-values which can be much higher, quite high, and reject the null hypothesis. Whereas for the separate bootstrap, as for the table quantiles, we get what we expect, namely that the null hypothesis is rejected. But even for the nested mean where the null hypothesis is actually satisfied, we get the right size for the separated quantiles, or the same size for separated quantiles as for the table quantiles, but for pooled quantiles we are too conservative. So the size is actually higher than nominal size. So yeah, that's all. Thank you.
Questions? Yes, Thomas.
Thank you. I have a question to both the speaker and the chairman. Would this theory of asymptotics and bootstrapping be applicable to the flags of barycentric subspaces?
Well, as I understand it, so as far as I understand it, the flags are not really an iterative procedure. So there you can actually have a more straightforward asymptotic theory, but I'm not sure if I'm wrong there.
I guess so. Now there's maybe the problem of having also charts for the flags is, I mean, in manifolds is not so easy, and that's one of the things that we try to work on with Stefan, but without full success. So it's but I don't think we fully need this theory, because it's already the object in itself on which you optimize.